In-office verification is an important aspect of successfully fitting rigid gas-permeable contact lenses. Lensometry is a key procedure associated with RGP verification. Mastering this instrument is easy with proper training and practice. A lensometer is used to verify the refractive power and optical quality of a lens. It can also be used to locate the optical center and to determine and measure prism. Although the lensometer has applications for both spectacles and contacts, this program will feature rigid gas-permeable contact lenses. Your own instrument may differ, but the procedures you are about to see and learn are essentially the same for all lensometers. A lensometer is used to verify a new prescription prior to dispensing, during follow-up care, or if a patient reports a change in visual acuity. The lensometer measures sphere and cylinder power in diopters. Cylinder access is measured in degrees. Begin by thoroughly cleaning the lenses to be measured and blot dry with a soft lint-free cloth. Move the lensometer into the upright position. Turn on the power switch. Preset the ocular to your vision correction by placing the power wheel at plano or zero power and turning the eyepiece fully counterclockwise. While looking through the ocular, slowly turn it back clockwise until the reticle scale is focused and stop. Position the small diameter lens table on the instrument. Center the lens with the concave or back surface against the lens table. It can be gently held or allowed to rest. This orientation permits the back vertex power to be measured, which is most often referenced when specifying a contact lens prescription. Roughly focus the target and center the green lines at the center of the reticle scale. This allows the optical center of the lens to be measured. You are now ready to measure the lens. Starting from the most plus position, simply turn the power wheel in the direction that brings the illuminated target into focus. The thin set of lines is called the spherical mire. The thick set of lines is called the cylinder mire. Notice that both sets of lines are in sharp focus. This indicates the lens is a single power or spherical lens. The power is the same in all meridians. Read the power directly off the calibrated wheel. In our example, the spherical lens is minus 4.75 diopters. With a toric lens, the target lines 90 degrees apart must be brought into focus separately. A toric lens has two different surface powers located at right angles to each other. Readings must be taken at each focused image. There are three types of toric lenses: back, front, and bitoric. A back toric lens has two powers on the back surface and a spherical front surface. A front toric has two powers on the front surface and a spherical back surface. A bitoric has two powers on both the front and the back surface. To determine the power of a back toric RGP lens, start with the lens centered on the lens table. It's especially important to measure a toric lens at the optical center to obtain accurate power readings. Adjust the power wheel in the most plus position. Turn the power wheel until either one of the meridian lines begins to focus. With your free hand, rotate the lens table simultaneously with the power wheel to achieve optimum focus. In our example, the power displayed on the calibrated wheel is minus 1.5 diopters. Record the reading. Now, turn the power wheel until the other meridian lines achieve focus. In our example, the power displayed is minus 3.75 diopters. Record the reading. Note the two different powers. The lens measures minus 1.5 and minus 3.75 diopters. All back toric and bitoric lenses are recorded in this manner. The power values are taken right off the drums. There is no axis reference. Our next example is a front toric lens. A front toric lens has two powers 90 degrees apart on the front surface while the back surface remains spherical. Center the lens back surface on the lens table. Position the axis knob at 180 degrees. Locate one of the power meridians by adjusting the power wheel until a rough focus is achieved. Then, rotate the lens until the Myers indicate that the lens is positioned with the prism directly at the bottom. Recheck to be certain the lens is still centered on the lens table. Rotate the power and axis wheels simultaneously until the spherical Myers focus. Minor adjustments of the power and axis wheels assure accurate readings. Record the power reading for the sphere. The power is -8 diopters. Rotate the power wheel to focus the cylinder Myers. Record the reading. The power is -7 diopters. Make note of the axis reading, 15 degrees. Front cylinder lenses are recorded in spherocylinder form. The amount of difference between the two powers is the cylinder power of the lens. The difference between -8 and -7 diopters is +1 diopter. Record as -8 +1, axis 15. Our next section features RGP bifocal lenses. Bifocal RGPs are primarily of two designs, annular and segmented. For an annular bifocal, measure the power first through the optical center of the lens. The distance power is -1 diopter. Reposition the lens to one side to read the power in the periphery and refocus. The power is +4.25 diopters. The add power is the difference between the two findings, +5.25 diopters. With a monocentric prism ballasted segmented bifocal, position the lens so the segment line is across the center of the aperture. Distance and near power can be read by rotating the power wheel. No repositioning is necessary. The image for each power appears at the same location. The add power is the difference between the distance and near findings, +1.75 diopters. Any jump in the image from one focus point to the other indicates a bifocal lens that doesn't have monocentric optics. This lens has a jump of ½ a prism diopter. A lensometer can also be used to verify and measure prism. Carefully center the lens on the lens table and focus the image. Prism power is determined by the amount that the target lines are decentered in relation to the center of the reticle. Each ring represents 1 prism diopter. In our example, the amount is 2 prism diopters. Look for lens prism even if it was not specified in the prescription. It can result from poor manufacturing. A distorted or difficult to focus target image may be the result of a dirty lens. Proper cleaning will significantly improve the image. Poor optical quality. A hazy or distorted image may indicate a manufacturing error. These are the primary procedures for using the lensometer. In review, always center the lens on the lens table. Find the most plus position reading first, and then measure in the minus direction. Take multiple readings of each lens to ensure accuracy. The meridians of a spherical lens focus simultaneously, torics independently. Cylinder value is measured as the difference between the spherical and cylindrical meridians. Proper RGP verification is an integral part of the successful RGP lens practice. With periodic review of this program and practice, you can maintain a level of skill with the lensometer which will assure better lens fitting, quality, and patient comfort. Refer to other programs in the CLMA and RGP Lens Institute video library. These videos are designed to assist eye care professionals, assistants, and students toward the improved fitting of RGP lenses, including keratometry, verification, modification, and the radioscope.